A very good day I bid to everyone. For this integrated project, our group has selected the crude oil refinery plant to conduct the process safety analysis, wastewater treatment plant, and identification of the air pollutant from the plant. The group member consists of Cindy, Wong, Eunice, Darren, and Victor. My name is Eunice, and I will briefly introduce about the crude oil refinery process plant and the hazard analysis. To start with, I will briefly introduce the background of oil refinery industry. Crude oil is a complex mixture of different hydrocarbons and varying amount of other compounds containing sulfur, nitrogen, oxygen, as well as salt, trace metal, and water. An oil refinery plant is an industrial plant that transforms or refines crude oil into various usable petroleum products, such as diesel, gasoline, and heating oils like kerosene through a series of physical and chemical separation techniques. These techniques include fractionation, cracking, hydrotreating, combination, or blending process, and manufacturing. During the oil refinery process, one of the hazardous material that has been identified, which is the hydrogen sulfide. There are three main generations of the hydrogen sulfide, which is naturally generated in situ from the reservoir biomass. Besides, it may be generated by the conversion unit cracking feedstock containing sulfur, and lastly, from the hydrotreater that specifically focus on removing sulfur by creating hydrogen sulfide. We have selected the Pengerang Integrated Complex, which can be denoted as PIC, to carry out our study. PIC is the largest downstream greenfield development in Pengerang Kota Tiki District, Johor, Malaysia, which spans over an area of 80 km². PIC houses oil refinery, naphtha crackers, petrochemical plants, liquefied natural gas terminal, and a regasification plant. From the research, there were two noticeable population or residential areas located near the plant, which is Kampung Sebong and Kampung Sungai Bunang. Apart from that, hazard analysis has been carried out on the selected equipment, which is the storage tank. Firstly, the parameter node is the flow. More level in storage tank may be caused by the top tank unattended, the level indicator failed, and the wrong valve open. While less level in storage tank is caused by cracking or corrosion of the tank, damage of the tank body seal, weak joint, damage of a valve, rupture of a tank due to integrity loss. More level and less level in the tank will lead to crude oil leakage to the atmosphere, which may initiate the fire if any ignition source exists. Consequently, this may hit the nearby tank or cause burn to worker due to exposure to heat radiation. Corrective action that can be taken is install level meter and high temperature alarm.
Hi, my name is Kong Chi Chai, presenting the case study of process equipment. For this project, the equipment that we chose is fixed roof tank, and the hazardous material identified with Ting is hydrogen sulfide. We have made several assumptions. The temperature is 130 degrees Celsius. The volume inventory is 3,975 meter cube, and the pressure is 10 bar. The weather during the day is 1.5 meter per second under Class A, while for the weather during the night is 1.5 meter per second as well under Class F. Two types of worst case scenarios have been assumed, which are leak with orifice diameter of 5 mm and catastrophic rupture. And here are some of the additional information needed when we are simulating the fast and safety software, such as the ambient temperature, the relative humidity, the winds data, the event frequency, the emission data, and the fraction of population indoors. For the first case, based on the consequences summary report, the peak flow rate of hydrogen sulfide will be 0.04 kg per second for both day and night weather, and 3,600 seconds are needed for the leaking to stop. The radiation versus distance for jet fire graph, the radiation level increases until a peak level of 0.54 kilowatt per meter cube at 2 meter. Moving on to the downwind vapor concentration, the graph of maximum concentration versus distance and graph of concentration versus time at a given distance are attached here. For the cloud footprint, the blue line represents the weather category of 1.5F, while the red line represents the weather category of 1.5A. Moving on, there is no explosion case happening for the leakage scenario for both of the weather categories. Thus, the process plant around is safe from the occurring of explosion worst case due to the leaking. For the flash fire envelope, the maximum flash fire distance due to leak for the weather category of 1.5F is 1.72 meter, while for 1.5A is 1.61 meter. The distance for both weather categories is almost similar. The second case, based on the consequences summary report, the distance to UFL and LFL for both weather categories are shown in the picture here. For the downwind vapor concentration, Graph of maximum concentration versus distance and graph of concentration versus time at given distance are illustrated here. On to the cloud footprint, the gas cloud is able to spread a downwind distance of around 130 meters for both weather categories. The blue line represents the weather category of 1.5 F, while the red line represents the weather category of 1.5 A. Since the hydrogen sulfide leakage will cause a huge impact on human health within that distance, the process plant should be evacuated to avoid the hazardous effect. Next, the maximum diameter of worst-case explosion could be up to 2,000 meters of the downwind distance for both weather categories, and it is big enough to affect the residential area around the process plant. For the explosion overpressure, at 40 meters of distance downwind, it achieved the highest overpressure and started to decrease rapidly after 60 meters of distance downwind. The data and summary report for explosion is attached here as reference. For flash fire envelope, the maximum flash fire distance due to catastrophic rupture for the weather category of 1.5 F is 61.4 meters, while for 1.5 A is 59.9 meters. Lastly, for the intensity radii for fireball, the fireball diameter will be 207.9 meters. The distance downwind to intensity level 1 is 440.8 kilowatt per meter square. 246.9 kilowatt per meter square for intensity level 2, and lastly 124.9 kilowatt per meter square for intensity level 3.
Hi, my name is Darren and my ID is 190013551. I will be presenting for Chapter 4 and Chapter 5. Before conducting the fault tree analysis, we assume 1 year of operation for all equipment. The data and calculation are attached in the appendix. For scenario 1, the leak cache of fixed roof 10, the data were retrieved from textbook before conducting the fault tree analysis table. The right side shows the fault tree analysis for scenario 1. The second fault tree analysis was conducted for catastrophic rupture of the fixed roof 10, and the right side also shows the fault tree analysis for its scenario. In Chapter 5, the simulation was done in safety software, and the table shows the result obtained. Table 5.1 shows the upper limit for LSIR in Malaysia. Individual risk means the total risk to a specified individual from all hazards to which the individual is exposed. The risk for outside office was only 4.28 to the power of negative 6, whereas the risk for inside office only 2.5 to the power of negative 6. When comparing with Table 5.1, it shows that it lower than the tolerable risk level for worker on site. Thus, the workers are safe from incident. IRPA can be calculated by the formula LSIR multiplied with the exposure in the unit of year. The value calculated are same as individual risk, so the workers are also safe from the accident as well. Next, LSIR refers to the annual probability of dying as a result of the major accidents analyzed for a person remaining permanently in a given spot. From the figure shown, the people in pink line are under tolerable risk level for residential receptors, which is unacceptable. The remainder of line are still in ALARP region, but preventing actions must be performed to enhance safety and lower the risk to a manageable level in accordance with standards. Societal risk is typically presented in FN curve, which will be explained after this. The residents around the Kampong Sungai Buntu residential will be affected since they live nearer to the plant. If catastrophic rupture or leakage of hydrogen sulfide happens from the fixed roof tank, they have high chances to expose to the explosions and the toxic gas, which will threaten their life. The societal FN curve shows the curve relating the probability per year of causing n or more fatalities. Yellow line represents the minimum criterion lines, where the red represents the maximum criterion lines. Since the total risk line fluctuates above the red line, so there's an unacceptable risk. Potential loss of life refers to the expected number of fatalities within a specific population per year. The loss of life for both indoor and outdoor are very less, which are only around 1 to the power of negative 5. Thus, the number of deaths is very low. People are safe from the incident.
Moving forward, I'll be discussing the result of possible risks to the area that is highly occupied, which is within the production plant and the closest residential area to the production plant. Firstly, for the highly occupied area, since the downwind vapor concentration is up to 450 meters within the plant, worker within the plant who does not equip with PPE will be greatly affected. Besides, the region within radius of few meters of the south of Pengerang Integrated Complex are exposed to the risk over the top tolerable limit. And lastly, the industrial area is exposed to significant flammability and toxic. For the closer residential area affected, flue-blown plant explosion which cause the chemical leakage will cause air pollution, damage of internal organ. Apart from that, the release of flammable toxic gases causes explosion and fire burn. Last but not least, the downwind concentration of hydrogen sulfide gas to residential area causes irritation to eyes and respiratory system. To summarize, from leakage worst case scenario, glass cloud could spread huge downwind distance at night as compared to daytime and there will be no explosion risk. While for catastrophic rupture worst case scenario, glass cloud could spread huge downwind distance at both night and daytime and there will be risk of explosion. From the fault tree analysis, the potential incident frequency of leakage and catastrophic rupture for storage tank are 0.94 at 5 and 0.0 at 76. Therefore, it can be concluded that the storage tank has the less likelihood of catastrophic rupture compared to leakage. The individual risks, the industrial area and several parts of residential area are not in the Anak region as it is under acid 1 to the power of -5 fatality per year limit with high flammability and toxic risk. The observation above, some strategy required in order to minimize the risk that could affect major area of production plant area and also residential area. First of all, since the storage tank is used to store highly hazardous material, we can replace the tank with more First of all, since the storage tank is used to store highly hazardous material, we can replace with storage tank that is compatible with the stored chemicals such as mild steel, stainless steel, and cross-linked HD polyethylene. Other than that, layer of protection analysis need to be analyzed from time to time in order to improve its effectiveness in terms of contaminant and control, as well as preventive and mitigation action by combining, substituting, minimizing, moderating, and simplifying solution. Inherently safer design must be considered. Next, storage tank use must meet the technical standards such as hydraulic calculation and physical property to prevent tank leakage. Addition of gas detector and water sprinkler can be applied to the storage tank to prevent leakage and explosion of the tank. Last but not least, regular maintenance and emergency evacuation plans should also be developed with clear instruction.
Hi, I'm Cindy Lau Jen Ding, and I am going to introduce potential conceptual designs for wastewater treatment plant at Pengerang Integrated Complex in Johor, Malaysia that incorporates with elements of sustainability that considers economy, social, and environmental aspects. VI Tech Wabat Company is responsible to establish a new effluent treatment plant at Pengerang Integrated Complex under the contract. The proposed effluent treatment plant consists of a two-stage primary treatment, followed by equalization, two-stage biological treatment, and tertiary treatment such as advanced oxidation process, ammonia stripper, and dryer installation for sludge treatment. Primary treatment is used to separate sludge from water through gravity separation, which is a physical operation that removes the floating and settable materials in the wastewater. Primary treatment for refinery wastewater is divided into two stages. At the first stage, American Petroleum Institute API separator can simultaneously remove both heavy oil-bearing sludge and lighter insoluble oils from water due to the differences in density. For the secondary stage, dissolved air flotation DAF unit or induced air flotation IAF unit are used for further removal of oil and fine solids from the effluent from the primary stage. Since there is sudden change of flow or composition in the wastewater treatment plant causes the fluctuations to occur. Therefore, equalization system is required to reduce the fluctuations by dampening the flow variations. This leads to a reduction of potential spikes in flow and loss to the downstream units. In terms of economic consideration, it also reduces the size of downstream units and the cost of the overall refinery wastewater system. In two-stage biological treatment, the first activation stage is operated with high sludge load due to the oxygen consumption of microorganisms through the oxidation of organic compounds and consequently the fertilization of carbon compounds in the foreground. Whereas the remaining carbon compounds are broken down and the nitrogen compounds are oxidized in the second activation stage, which is generally operated with a low sludge load. The reason why using two-stage biological treatment is because it can produce better quality of effluent compared to the single-stage biological system, and it can reduce approximately 30% of the tank volume. Next, come to advanced oxidation process. It is a tertiary treatment process used to remove organic pollutants in water by oxidation through reactions with hydroxyl radicals. Precise pre-programmed dosages, sequences, and combinations of ozone and hydrogen peroxide are applied to obtain maximum yield of hydroxyl radicals. As a result, a higher percentage of the pollutants is mineralized in the reaction tank. Advanced oxidation process has environmental sustainability as it can effectively clean the biological toxic or non-degradable materials, and it can reduce the toxicity of the wastewater. For ammonia stripping process, it is a process by which wastewater is contact with air to strip the ammonia gas present in the wastewater. In this case, semi-batch jet loop reactor is designed to remove ammonia from the wastewater through the utilization of the kinetic energy of high-velocity liquid jet to enter the gas phase, besides producing fine dispersion between the gas and the liquid phase. When comparing with classical reactors, semi-batch jet loop reactor has more advantages with respect to performance and yield, such as simpler and lower construction and operational costs, much more flow circulation over the classical reactors under the same energy input, high level of gas dispersion, high mass and heat transfer availability. It can also achieve very high percentage of chemical oxygen demand removal, which poses the capability to operate at high biomass concentrations. Therefore, semi-batch jet loop reactor is said to have economy and environmental sustainability. Sludge drying is a thermal drying process where thermal energy is provided to the sludge to evaporate water. Thin film sludge dryer is used to reduce sludge volume by decreasing the liquid content and increasing the solid content of the sludge. Heating fluid flows on the outer heating surface and the heat is indirectly transferred to the sludge film to remove the moisture from the sludge. As a result, the process reduces the environmental impact and produce a stabilized dry granular product that is easy to store and deliver, as well as suitable for agricultural use. This successfully fit the environmental and social sustainability.
Hi, my name is Victor. I'm going to be presenting the regulations and standards and the air pollutants of the industry. There are a total of 4 main regulations and standards, which are the Petroleum Development Act, the Petroleum Act, the Environmental Quality Act, and the Gas Supply Act. The Petroleum Development Act provides for exploration and exploitation of petroleum, whether onshore or offshore, by a corporation. This act also controls the carrying on of downstream activities and development related to petroleum and its product. On the other hand, Environmental Quality Act 1974 makes provision for the prevention, abatement, control of pollution, and enhancement of the environment, and for purposes connected therewith. Moving on to the Petroleum Act 1984, which exists to consolidate laws related to safety in the transportation, storage, and utilization of petroleum. The Gas Supply Act 1993, on the other hand, provides for licensing of the supply of gases to consumers through pipelines at controlled prices. The 2 main air pollutants from the industry are volatile organic compounds (VOCs) and ozone (O3). Volatile organic compounds are organic chemical compounds that evaporate easily at room temperature. The cause of volatile organic compounds in the industry are the burning of fossil fuels. Storage tanks justify substantial VOC emissions at petroleum refineries, even if they are furnished with floating roofs. They typically contain elements such as hydrogen, oxygen, fluorine, chlorine, bromine, sulfur, etc., released from the burning fuels such as gasoline, wood, coal, or natural gases. The effects of VOC can initiate throat, nose, eye irritations, headaches, breath shortness, skin problems, fatigue, and dizziness. Elevated levels or long-time exposures may result in lung irritations, kidneys impairment, liver impairment, cancer, as well as central nervous system damage. Ground-level ozone is a colorless and highly irritating gas that forms just above the Earth's surface. It is produced when the 2 primary pollutants react in sunlight and stagnant air. These 2 primary pollutants are nitrogen oxides and volatile organic compounds (VOCs). These pollutants come from burning of coal, gas, and oil in the industry. Short-term contact with ground-level ozone may result in a diversity of respiratory ill health, such as lung damage. Long-term contact to elevated levels of ozone can worsen ill health, such as emphysema, bronchitis, asthma, and completely destroy lung muscles, leading to ultimately death.